Okay, uh, let us start then. So today we are going to discuss week 7. So week 7 is welcomes you to the part 2 of statistics 2. So before this, so till week 6 we have studied different kinds of distributions, discrete distributions, what is the mean of that distribution, variance, standard deviation, CDF, PDF and everything. Also the continuous distributions, we have seen some common distributions and we have used some algebraic operations performed on those. We have seen how those distributions look like. And till week 6, we just taken care of looking into distributions. Now we enter into the actual statistics part, and this is the part 2 of statistics. So today we will be discussing week 7 activity questions or practice assignment questions.
Excuse me, sir.
We share my screen. Yeah.
Sir, one more open session are we conducting for week 7 on 14th?
On I'm not that sure. Did you got any message
Sir,
regarding that?
it's on my calendar. It's written week. It's not written any week there. It's just written open session for statistics 2 on 14. It's on my calendar.
It's on 14th, is it? It's on Monday. Is it on Monday? Yeah. So maybe yeah.
Yes, sir. It's on Monday.
Yeah. So yeah, we have converted one open hour session into open session, I guess. So I'm not sure. I just mailed to support team and confirm.
Sir, it's for week 7 or it's for the whole
If
1
it
to 6?
is there, it will be week for week 7.
Okay, sir.
Okay. Yeah. Is it like do you have
Sir,
any before week 6 kind of thing?
sir, I haven't watched this week 7 lectures yet. It should be helpful if I go on participate in this meeting, or do I need to watch this to understand the current lecture, the current meeting?
You have a doubt in week?
No, I haven't watched the week 7 lecture. Will it be helpful if I go on continue this session, or it is mandatory to watch the session?
Uh, this is not a mandatory to watch the session. You just do one thing then. Just go watch the lectures and then come back to this session and look at some of the activity questions. Difficult activity questions I will be solving in this session and some practice assignment. Or if there are any doubts in the lectures, I can simply elaborate those. Okay.
So will you be just handling questions or will you explain?
If there are no questions, then I will take some explanation kind of thing, like some. If you are
Okay, sir.
feeling some difficulty in understanding one lecture, I may take up that lecture and I may.
Venkatesh,
Okay.
I have doubt in lectures 7.6 and I mean 7.6, 7.7 and
Okay.
7.8.
Okay.
And I have the timestamp with me. Do you want to
Okay.
write
We
it
will
down right
discuss that.
now? Or yeah, okay.
Okay. Let me take the questions first. If there are no such questions, we will move to the lecture.
Sir, I have doubt in question number 6 and 7 from activity 7.2.
6 and 7.
Yes, sir.
Sir, in question number 2 also, 7.2,
7.2. Okay.
and the last option, last question, 7 number.
7 I have already written.
Okay, sir.
Okay.
So
What about 7.4?
7.6 question 1 and 3.
Okay. 7.4, 7.5, 7.7. Practice assignment. Okay, one more minute. Just think. If there are no, I will just explain these 5 questions and I will move to the lecture video explanation.
So Venkatesh, alongside, for example, 7.6, when you take the question, you might want to take the lecture portion also,
Yeah,
because
sure,
then it
sure.
will be in flow.
Right. I will take it in
Yeah, fine.
that
Okay.
manner. Okay, then
So in
without further delay.
7.6, 7.7 and 7.8, all the three.
Yeah, sure.
Okay, fine.
So, okay. Let me deal with the first 3 questions of 7.2, which are question 2, 6 and 7. And later we will move directly to lecture 7.6 and later we will solve the questions 1 and 3. Then we will move to 7.7 and 7.8.
Excuse me,
Okay.
sir.
Yeah.
Sir, I have not yet completed this 7.7 and 7.8, these 3 lectures in the last. So if the upcoming session would be on clarifying the doubts regarding these activity questions also. So
Yeah,
it
yeah.
would
See,
be
that is an open session. You can ask any question in that.
okay.
Even the
Okay,
lecture
sir.
video questions can also be asked in that. Even the activity questions you can also ask in that.
Okay, sir. Thank you.
Okay. Yeah. Okay. Then let me see what is question number 2 in 7.2. Okay. Okay. So
Sir,
there are some. Yeah.
in question number 2, I have doubt in option number 3.
Okay. Okay. What is your take on this? It should be correct or it should be wrong?
It should be wrong, but in answers it's given as is correct, accepted
Okay.
answer is.
Okay. Why? What is your explanation for the option 3 to be wrong?
As n increases, sample variance goes to 0, na sir. Variance.
See, variance of that particular variance goes to 0. Right. See, what is the sample variance here? Sigma square by n. Right?
Yes, sir.
Okay, as n increases, sample variance takes values close to distribution variance. Okay. As n increases, variance of the sample goes to 0. But is this not the direct statement which was mentioned in the lecture?
In lectures, they said that as n increases, the variance goes to 0, na sir.
Okay. Yeah. So as n increases, sample variance goes to 0. Correct.
It's for expected value. Expected value goes to mean, distribution mean.
Expected value.
As n increases, expected value goes to
Yeah.
distribution mean.
Right.
Yeah, instead of distribution variance, it should be mean.
It
So
should be mean. Yeah.
I think
The value is close to mean. Okay. Yeah. Yeah. Good point. Valid point. Right. I see. This is the sample variance. As n increases, sample variance takes values close to distribution. Okay. What is variance of s square?
X1 minus x mean, sample mean square. Like that for up to xn.
Okay. So s square is given to be x1 minus mean square. Okay, I will write simply summation I takes 1 to n xi minus x bar whole square by n minus 1. So this is the sample variance, right?
Yes, sir.
Now as n increases, what happens to this s square? S square is the sample variance. No? So this is
It
same as
decreases.
it is same as asking as n tends to infinite, or as I increase the value of n, where will this s square go?
0.
Will it go to 0?
Here I have one doubt, sir. Like if n also increasing, the xi also keep on increasing, right?
Right. Yeah.
Then how it goes to 0?
It won't go to 0. Yeah, I was wrong there. See, sample variance is s square here. We define s square as summation xi minus x bar whole square by n minus 1. So as I keep on increasing this value n, what happens to my s square? Where will this tend to?
It decreases.
Uh, can I
No, it won't
say?
decrease.
Can I
It
say one point?
approaches to sigma square. So that is what that statement says.
Yeah, can I say one point? Like if n means if it is data points, if data points are keep on increasing,
Yeah.
that sample it is no more sample. It is going to be a data set. Then it is going to be a data set variance, right?
Distribution.
Yeah.
Right.
Is it for one sampling only, na?
This is for one sample. See, if my n is 10, if I consider my n to be 10, I take 10 samples, 10 random samples from my distribution.
Yes.
So for that 10 samples, I will get some sample variance, right? S square. If I compute this, I know the mean of it.
S square is only one sample.
Huh?
Only one sample. S square.
But sir, mean here the mean is sample mean is for the different sampling, na, sir. It is for different sampling we are calculating this mean, x mean.
See, this x bar is summation xi I to n divided by n. Even this x bar depends on n. Okay, as I keep on increase the value n, my x bar will take value closer and closer to mean, distribution mean. Will you agree with this?
Yeah.
Yes, sir.
Yeah. If I have more data points with me, my sample mean will take closer and will take closer values to expected mean, to the distribution mean, which is mu. As n increases, my x bar will tend to
Mu.
Okay.
Yes.
Similarly, as I increase n, what happens to my sample variance? Even the variance of the sample, what will happen to my sample variance? If I have some 10,000 data points where my n is 10,000, okay. So if I compute the sample variance of it, it will take closer value, closer to sigma square than if my n is some 10 or 20. Did you
Yes,
get
sir.
the point?
Yes, sir.
So we are not dealing with this sigma square by n. Okay, this is just the variance of this sigma square.
S square.
Variance of s square.
Yes, I get the point, sir.
Okay, so this
Yes,
particular variance goes to 0. Variance going to 0 means that particular s square will come nearer to variance is 0 means there is no much difference between the original distribution variance and the sample variance. So the sample variance comes closer and closer to the original distribution variance, right? This particular
Yes,
s
sir.
square comes closer and closer to sigma square. Therefore, variance of s square will go to 0. Okay.
Yes,
Will
sir.
you
I
get
thought
it?
this as a mean of variance of sample mean.
No. Yeah, you are talking about variance of sample mean. A
Yes,
sample.
I took it as that.
So this is not variance of s square. Even this is variance of x bar.
Yes.
Hmm?
Thank you, sir.
Yeah. Okay. What happens to question number 6? So what is question 6 here? Okay, a certain type of thread is manufactured with a mean tensile strength of 65 kilograms and a standard deviation of 6 kilograms. How is the variance of the sample mean change when the sample size is increased from 100 to 256? Okay. So in that question, just identify what is the distribution mean, which is mu, what is the distribution variance, which is sigma square, and then once you identify these two, then identify uh, what is the size of the sample. So what is n1, what is n2. Once you identify what these values are, it will be easier for us to solve. So it is given that a certain type of thread is manufactured with a mean tensile strength of 65 kilograms. So when they are saying mean tensile strength, so that will be our distribution mean. So there are some threads being manufactured in a company. So each thread will have a tensile strength, different tensile strengths, but on an average, the tensile strength is of 65 kilograms.
But sir, how to recognize that the given mean is the distribution mean or the sample mean?
See, we said directly, right? A certain type of thread is manufactured with a mean tensile strength. So if we are talking about some company or something manufacturing with a mean tensile strength, it takes all the data before you are manufacturing the 1 lakh thread. So it will take all the 99,999 data and compute the mean, and it is shown as the mean of the mean of tensile strength. So that
Sir,
means,
can you give any example for sample distribution, sample mean?
see, we will mention it directly, right? So we will talk from this distribution. We have taken a sample. Until and unless we mention sample, it represents the whole data only.
Okay, so if the sample is not mentioned in the question that the given mean is sample mean, then we'll consider it as distribution mean.
Yeah.
Okay.
See, we never said a certain type of thread is manufactured and some sample is taken out with a mean of tensile strength of something. So it should have been like that question. If
Okay, sir.
we were about to talk about sample means, the question might have framed like that. Okay.
So here it is
Okay, sir.
population mean.
Yeah, this is the total distribution mean. So once you identify these things, so this will be 65, this will be 36. So sigma is given as standard deviation is given as 6, so sigma square will be 36. N1 is given to be 100 and N2 is given to be 256. Now what we have to do is, so you know expectation sample mean, right? No need of how is the variance of the sample mean. So we are worrying about variance of x bar. So variance of x bar, we know that it will be sigma square by n, right? So for this it will be sigma square by n1, and for this it will be sigma square by n2. So just compute these values. We know these values as 36 by 100, and this is 36 by 256. So this will be 0.36. So from the options you can see
0.14.
this will be much lesser than 0.36. So I'm dividing it by 256, which is greater than 100. So it will be lesser. The value will be lesser than 0.36. If you compute this, you get something around 0.14. So you can see here from 0.362 it decreased to 0.14. Right? From 0.36 to 0.14, the value is decreasing. Initially it is 0.36. Now the value decreased to 0.14. So now also you can see as the number of data points is increased, my variance of sample mean decreases. So that means the sample mean and sample means goes closer and closer to distribution mean. Okay. Same thing for seventh question also. Even in the seventh question, it's just like we just change the n1 and n2 here. So now n1 becomes 625 and n2 becomes 64. Just compute the values, you will get something around.
Okay,
So
sir.
now n1 and n2 from n1 is greater than n2. So I hope variance should decrease. So either A or C should be the answer. Okay.
Yes, sir.
So just compute the values, you will get. So once you get the values, it will be A or C. Let me check the answer.
Here I have one doubt, sir.
Mm.
Like if n is increasing, does variance also needs to be vary, right? Like for 100 also it is showing sigma square 36 and 256 also
See, the
plus
sigma square
36.
is constant for distribution. These are sigma. This mu and sigma square is for population. Population.
Okay.
Okay. So these are samples. So out of those population, we are taking some subset of some subset sample. So for the first sample, we have taken 100 samples. For the second, we have taken 256 samples from that distribution. Okay, random sample. So the distribution is constant. So it won't change.
Sir, one question.
Okay,
So for sample mean, we denote it by x bar.
X bar.
Okay, okay, sir.
Yeah.
Sir, I have a doubt.
Hmm.
For distribution, mean
Okay.
and variance.
Distribution, mean and variance.
Variance. What is the difference? Why do we use either distribution mean and variance or the data mean and variance?
Why do we use?
Either, I mean, why do we consider, like when we say it is distribution mean or variance, if we already have that, in that case, why do we need the distribution? Sorry,
Sample means and
sample mean, and yeah, because we already have it for the population. Then how
see, to
is
validate the data. See, once you know that is the mean and that is the standard deviation. So if you wanted to validate the data, or
okay? So it is mainly to valid. The main purpose is for validation.
yeah, as far as my point of view, it is for validation also. And
Because I'm getting confused with why do we need and what's the application of having separate mean when in cases when we already know the mean and
okay, so
standard
see,
deviation for population.
okay, maybe this might also be one reason. So always you cannot deal with the whole distribution, whole data points, right? So
Hmm.
if you wanted to, once you know that distribution and everything,
Hmm.
so let's say this distribution is something like if I wanted to buy some plots in Chennai,
Hmm.
and I know average cost of 1 square feet of the land in Chennai. Okay,
Hmm.
it differs from different areas, right? So at some area
Right.
it will be different, and the other area it will be different.
Hmm.
But on an average, I know on an average, I say it will cost around some 10,000 for 1 square feet
Hmm. Hmm.
at
Hmm.
one place. Okay, on an
Hmm.
average, this is distribution mean.
Hmm.
But if I am taking if I wanted to buy only 4 plots in 4 different locations,
Hmm.
now I should see. I know at one area it is 8,000. One plot is 8,000 for 1 square feet, and another place it is 12,000, and another place it is 6,000, and in another place it is something only 4,000. So
Hmm.
now I have a sample with me, not the whole distribution. How do I validate, or how do I check whether I am paying the right amount, or if I am,
Right. So basically, you just those set of data which have some kind of similarity in terms of its properties,
yeah, in
properties
terms of
sense.
properties.
Hmm.
So I can't deal with the whole data every time, right?
Hmm. 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 Hmm.
So
Got it, sir.
that is why, that is as of now I can think of these only. So if I get something in the next session or somewhere,
Yeah, sir. Makes sense. The scenario which you mentioned, it makes sense.
yeah.
Yes, sir, like OEM or any manufacturing companies.
Hmm.
So suppose they are producing bearing or shaft or anything,
Hmm.
and
Hmm.
they
Hmm.
want to control the quality and
Right,
from
right,
4
right,
sigma to 6 sigma. So again they sample out some random
right,
components and again they do same
right,
thing.
right, right, right.
So
Yeah,
it
yeah,
will
yeah,
be
true.
for that.
Hmm.
Yeah.
Hmm. Hmm. Hmm.
Thank
Thank you
you.
so much. Thank you. Thank you.
Okay, so let us move to 7.7 then, if there are no doubts in this. Okay. So yeah, in 7.5 there we discuss something related to concentration phenomena. Don't stress on that thing. If you are unable to understand that also, it's okay. Move on to the next topic. So
Sir, I have a doubt in 7.5 in at the timestamp 18 minutes, where the sir mentions the upper bound of the MGF. I'm not able to get where did he get the upper bound?
is it something related to Bernoulli thing?
Yes, sir. Yes, sir.
Something like, okay,
E raised to power minus lambda
right,
by
right.
2
Yeah,
plus,
I remember.
and that's upper bound is e raised to the power lambda squared, something like that.
MGF of, so we are trying to find the MGF of Bernoulli.
Yes, and I didn't get how did he got the upper bound.
Yeah. So once you compute, you know, the Bernoulli half will be, MGF of this Bernoulli half will be mx. Yeah, just a second. So, mx of lambda will be e to the power lambda by 2 plus e to the power minus lambda by 2 divided by 2, right? So this will be the moment generating function for Bernoulli half. So now for this, he has created an upper bound, right? He has created something like e power lambda square by 4, is it? Is it this?
Yes, sir.
Yeah, you want this thing.
Yeah. How did he get this one?
Okay.
Just a simple explanation would do.
What will I get if I derivate it by lambda of 1 by 4? Okay. Just give me 1 minute.
Mute everybody, sir. Some noise is coming.
Yeah. No, that is behind in my home. One second. Yeah. Okay. Have you plotted this particular function e power lambda by 2 plus e power minus lambda by 2 by 2?
No, sir. No, sir.
No. Okay. So what is Sar's explanation? Did he give any explanation, or he just said it will be less than or equal to e power lambda square?
He just told that it was the upper bound of this one.
Okay, just do one thing. As of now, just take lambda to be x and just plot these two functions, e power x by 2
Okay.
plus e power minus x by 2 by 2 and e power x square by 2, x square by 4, sorry.
Okay.
And just see whether one graph is above the other every time or not.
Okay, sir.
Okay. If it is happening, then this is true.
Okay.
If it is not happening, then we need to worry.
Okay, sir. Thank you, sir.
Sir, is there any formula, sir? Like, say, generally we tend to have the formula, no, sir, e power plus x minus x, likewise.
No.
So this is something we can only interpret by graphically and not any formula.
No. I guess what will come if I differentiate with respect to lambda? It will be something like 1 by 2 into half e power lambda by 2 minus half e power minus lambda by 2. And if I equate it to 0 and if I try to find the value of lambda, so this will give me the minimum value for lambda. This will give me the function where it ends the minimum. Okay, so yeah, in max 2 there are some functions, like there will be some, we will take some two functions and we will, what is
Sir,
it?
I checked the graph. E raised to power x square by 4 is above this moment
Above
generating
this thing
function.
every time.
Yes, sir.
Sir was
Yes,
telling
sir.
about the function of the 1 by x and e to the power x. The two functions,
Function of
Yes.
1 by x.
1 by x and e to the power x.
Yeah.
Sir was telling the both are positive functions
Mm.
in the context of this, but I could not understand the same relevance.
See, yeah. Max 2, in max 2 you might have seen sandwich theorem. Have you come across this term called sandwich theorem? See, there will be some
Yeah. Yes, sir. Yes, sir.
so we will, if you are unable to find the bound for one function, what we try to find is we will try we will get some easier function which is above this and some other easier function which is below this always, and we will say we will bound this particular unknown graph in between these two well-known graphs, and we will just sandwich that particular function in between these two functions, and we create some upper bound and lower bound like this. Okay, so
Yes,
that is why, yeah, see, there will be some standard graphs like e power x square by 2. So e power x square by 2 is a standard graph. So with
Yes.
that graph, we are just bounding this e power lambda by 2 plus e power minus lambda by 2.
Okay, sir. Okay.
So this is basically, sir, it is not like a formula or something. It's
No,
like
not like a formula. We are just bounding it.
okay.
Okay.
So, like, sir, for particular Bernoulli and these binomials sir has done, we have to note it down. Probably it may be asked in question.
It may be asked. See, the thing is, unless and until we stress something very in deep, we won't deal with that in particular. Okay. So that is
Okay.
why I said in lecture 7.5, if you, it is good to understand what is moment generating function. You will come across this moment generating functions in week 8 also. But you no need to worry about this concentration phenomena or calculating this probability of y less than or equal to expectation of y minus some t, or probability of y greater than expectation of y plus t kind of things. So if you are unable to get the bound by using Chernoff's also, it's okay. If you are unable to understand how to compute concentration phenomena is also okay. Just understand what is concentration phenomena, what exactly is happening, and in future if you have come across these kind of problems, then it is important that you know something about this.
Okay. So the funda is we should know that rather than 1 by x, 1 by n bound, this e to the power minus lambda bound is far better than 1 by x, 1 by n bound. That's the only thing we have to take out.
That's the only thing you have to understand from this.
Okay, sir. Done.
Instead of Chebyshев, Chernov's bound is much better. So for giving you that idea, we have introduced this concentration phenomena.
Okay, sir. Right.
Okay. Yeah. Okay. Then let us take some look at 7.7. So can I have the timestamp for 7.7 lecture or the whole lecture?
Sure. So, Venkatesh, it's 7.7 at 19.4.
Okay, at 19.4, let me just open that.
I understand, but wanted to confirm that particular thing.
Yeah. Let me just.
19.4. Yeah, sure.
Okay, 19 point.
19.4. 1904.
1904. Okay. Okay. So he's discussing
Sir,
something.
sir, before starting this 7.7, can I ask question from MGF? I have a little doubt.
MGF. Okay.
Okay.
Just give me 1 minute. Let me take a look
Okay,
at this
sir.
and I will come
Okay,
back.
sir.
Okay.
Yeah. Okay.
So what is he discussing there?
So he is discussing the sum of n IID exponential distribution.
Okay.
So what he said, sum of n IID exponential distribution is x raised to power n minus 1. So that n minus 1 was a bit difficult to understand. How come that became n minus 1?
Okay. So he's discussing something. Okay.
That is because we are not including the nth term, that is one term, right?
Sorry.
Just a second. Let me just hear it out from
Of them
professor.
together, if you add the distributions, the density becomes something like x power n minus 1 times e power minus beta. Okay, so that's the picture. If you take IID exponential distributions, okay, so let's say n of them, and then add them together, it turns out you get the gamma distribution with alpha being equal to n and the beta being the same beta. Okay, so that's an interesting property.
Okay. So he has just said that if I have some NIID exponential lambda, right?
Yes, right.
He just taken some of these things and he claimed that y follows gamma n gamma. What is beta? Beta being the lambda, right? So it is gamma alpha beta. So where he said alpha will be n and beta will be lambda. So that means he is claiming that. So okay, before he claims, we can prove it easily. So each of xi. So if I write the density function, so what will be the density function of this? Lambda into e power minus lambda x. Is it correct?
Yes, lambda e raised to power minus lambda x, right?
Lambda e raised to the power when x is greater than 0. Right? If I add all these things, so when y, now this will be lambda e to the power minus lambda x, x1 or x is fine, plus lambda e to the power minus lambda x, plus lambda e to the power. How are we getting there?
So it would be x1, x2, x3,
Yeah,
like,
yeah.
yeah.
So lambda of we are not going to get a closed form. Anyone, any thoughts? Okay, let us not use this. We will try to use the MGF of this. So what is the MGF of one generating function for exponential distribution? Anyone?
I won't be able to answer immediately.
Okay. So e power
Yeah.
lambda x. So it's just the expectation of e power lambda. So I'm just finding MGF of exponential distribution.
Yeah. So
Okay.
The probability of x and the power lambda x.
Probability.
yeah.
What is?
It is the probability of x.
Probability of x.
Then e power lambda x.
Okay.
Yeah.
You are saying the value.
PDF
Okay.
of X.
Okay.
Yes.
Yeah. So let me take the direct value. One by one minus. Okay, it will turn out to be 1 by 1 minus lambda x. So lambda sorry no, both became lambda here. Let us say exponential distribution with parameter beta. So now this will be 1 by 1 minus lambda beta. Okay. So see, this is just compute everything and finally you will get this. So if you have exponential distribution with parameter beta, your MGF will be 1 by 1 minus lambda beta.
Okay.
Okay, now you have MGF of your exponential distribution, and also you have NIID exponential distributions with you. And if I want to compute the MGF of this y, so what will that be? So how will I do that? Will it be the product?
Why will it be the product?
So because you see, when we are talking about moment generating functions are okay. Wait, let me just think for a while. So if I wanted to find moment generating function for this y, so what is the moment
Yes.
generating
Okay.
function? It will be expected value of e power
E lambda
lambda
y.
y. So what is y
Y.
here? E to the power
X1 plus X2
e
Xn.
to the power lambda x1 plus x2 plus and so on plus xn.
Yeah.
Now it will be e to the power expectation of e to the power lambda x1 times expectation of to the power lambda x2 times expectation of e to the power lambda x3 and so on expectation of e to the power lambda x.
And this is
Right?
happening just to be on the same page because it is IID, right?
Yeah, this is these are x1, x2,
This is
x3
the,
are all the
yeah.
IIDs.
Yes.
Now
Correct.
each x1, x2, x3, xn follows exponential distribution with parameter beta with mean 1 by beta. So I simply replace it with 1 minus 1 by lambda beta to the power
Beta.
n.
Exactly.
So this
N.
is same as this is equivalent to the MGF of gamma. So Sar has given MGF of gamma, if you remember. Some manipulations to be done. So what I can do is I can write this as 1 minus lambda beta whole power minus n.
Okay.
Now I can write 1 minus lambda by 1 by beta to the power minus n. Okay. Now you can see if I in the lecture also sir has given moment generating function for if x is gamma alpha beta, moment generating function of this will be 1 minus lambda by beta whole power minus alpha. From here you can compare. Okay, sorry, I am using the same thing. Let us take exponential distribution with lambda star. So this will be lambda star, lambda times lambda star. So this will become 1 by lambda star. So 1 by lambda star is the mean of the exponential distribution, right? So if you compare these two, you will get this particular distribution also follows gamma. This will y will follow now gamma n comma 1 by lambda star. That is what I got. Are we doing any mistake here or are we correct? Some mistake or any mistake? Just find, is there any mistake or
Here it is 1 minus lambda by
okay, my
1 by beta.
MGF, okay, my MGF of this is correct. So MGF of exponential distribution with parameter lambda star is correct. So this is 1 by 1 minus lambda times lambda star.
Lambdas, will it be parameter is lambda star, right? So it will be 1 upon 1 minus lambda star x, right? Not lambda star. It
So
will
this
be
is,
lambda star x. You are taking the parameter as lambda star, right?
yeah, I am taking lambda parameter as lambda star, and it's a function of lambda, right? Moment generating function is a function of lambda.
Yeah. Okay.
Okay. So
Okay. Fine.
this is correct. This is what I have done is correct. But we are getting okay. Okay, got it. Okay, this is lambda by lambda star. So I just use some textbook where he has given his parameters. See, that is why we shouldn't follow different textbooks. I said, see, some people will say parameter beta, parameter lambda for exponential, and they will take parameter as mean, and some will take as parameter as 1 by mean. So there he has taken it as mean. So if you find the MGF of it, just find the MGF of this by taking e power lambda x, where x is following exponential distribution with lambda star parameter. So here parameter is it follows exponential lambda star. So mean is 1 by lambda star. So we will get 1 by 1 minus lambda by lambda star. So with that, here we will get lambda by lambda star. So I will get lambda by lambda star. So lambda star. So if I compare this with this, I will get beta to be lambda star and then to be alpha to be n. So the same thing even professor also mentioned. If I sum all the IIDs of exponential distribution with the lambda with the beta, I will get the final distribution y to be gamma n comma beta. Okay, just use this moment generating functions. So validate this thing. If this is correct, then these are pretty straightforward steps to follow. So once you get to the final
I'll
step,
read your explanation with the lecture and then perhaps try to understand. I mean,
just
in the
cross.
interest of time, I'll take it offline and then get back in case questions are there on discourse.
Sure.
Sure. Thank you, Venkatesh.
So this is about 7.7 timestamp. Okay, let us discuss the questions which others has asked. So these are graphical questions, right? This particular lecture we have given graph of it. What are the questions? Question number? The one who asked left the session. Acha, is it 7.6? Okay, sorry. Okay, what is the timestamp of 7.6, Apul?
7.6.
Central limit 0.
I asked for 7.7.
7.7 and 7.8, is it? I got
7.7 and 7.8, right?
Okay, I
Yeah,
got
someone
questions
wanted to
from.
ask question from 7.6.
Okay, which question is that?
Someone else asked. It
Okay.
wasn't me.
See, yeah, at that point you said you can explain 7.6 and you can take the questions.
Hello, sir.
Yeah, hello.
Same Himanshu here.
Yeah, hello.
Sir, I wanted to ask you the difference between sample proportion and probability of that event that is in the sample proportion, because here it is mentioned that if n increases, then the expected value is same as the probability of that event. Isn't that independent of the value of n? Because sample proportion in itself by its definition is the probability of that event, right?
Probability of that particular event of that particular sample, given sample. See, if I have given you, see, if I am
Yeah.
Okay. If I have given you an experiment saying that you toss a coin, okay, you toss a coin 10 times.
Yeah.
So what is the my event is now my event
Heads or tails?
Heads or tails. So I wanted to find the probability of getting head. So what is the probability of getting head event?
It will depend as it will vary as a what binomial distribution. Okay. Sorry.
Okay. So if you know if you know initially it follows Bernoulli, then you can say probability of getting heads is half. So for that event, it is getting half. But when I actually do the experiment, perform the experiment 10 times, I'm not sure that I will only get 5 times head and 5 times tail. So you can get 6 times heads and 4 times tails. So when you get 6 times heads and 4 times tails, now my sample proportion will be 0.6, not 0.5. So like this, if I increase my n, so if I perform some 100 times or 1000 times, I will come closer and closer to 0.5.
0.5.
Which is actual probability of that event.
Yes, sir.
Okay.
Okay, sir. Thank you.
Okay. So let us see this 7.6 question number 1 and 3. Is the people there who asked these questions?
Yes, sir. Yes, sir.
Yeah. Okay. 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 7.6 AQ1. Sorry. AQ 7.6 question number 1. Okay. So what's the issue?
Sir, I'm not able to find delta of the question.
Okay. Okay, first let us start by step. The average life of a coffee machine is 5 years. So what is this average life of coffee machine gives me?
The mean expected value.
Mean or expected value. So I will note it down. Mu is 5. Okay. The next is with a standard deviation of 1 year. Right? So sigma will be 1. Correct?
Yes, sir.
Yes, sir.
Okay, once you get these two, assuming that the lives of these machines follow approximately a normal distribution. Okay. Now, if I say my x is the number of years that my coffee machine will work. So x is a random variable, and this particular random variable x follows normal distribution. Normal with the mean we know it as 5, with the standard deviation we know it as 1. Okay, so x is just the number of years my coffee machine work, and this is a random variable. So for each different coffee machine there will be different lifespan. Now find the probability that the mean life of a random sample of 16 such machines falls between 4.6 and 5.4. So see, a lot of terms came in one particular statement itself. So they are asking us the probability that mean life of a random sample. So there is a sample of 16 machines, okay, and we are worrying about the probability of mean of that life. So that means there is, you take it very simply. So I take a new random variable y, which is basically the sum of lives of all the 16 machines. So x1 denotes the life of first machine, x2 gives me the life of second machine, likewise x16 gives me the life of 16th machine. Now when I want to talk about the mean of this sample, what is the mean of this particular sample? What will be the mean?
5.
So 5.
Why?
5.
No. Mean of this particular sample. Mean of
5 raised to power 16.
Sigma square by n. 5.
Okay. What is the mean of this sample? Don't worry about this thing. I have 16
n times new.
six,
N times
n times
new.
Mean is x bar. Now we
Okay.
converted to sample. This
Acha.
is till here it is distribution. Now we have 16 samples. Out of those total distribution, now we have 16 different coffee machines in front of us, and we wanted to look at the mean of the lifespan of these 16 machines. So now what is x bar now? So
Sample
x bar
mean.
is mean,
Sample mean.
yeah, mean of
The sample.
16 samples.
yeah, mean of 16 samples. So what this will be equal to? So some total life by 16.
16. Yes.
Correct?
Yes.
Is this the mean? I have see now forget about the samples also. I have 16 observations. I just wanted to find the mean of 16 observations. What is the formula to find the mean of 16 observations? Sum of all the observations divided by number of observations.
Yes, sir.
Yes, sir.
Okay. The same thing also. The same thing works here also. So this is the total lifespan of all the 16 machines. If I wanted to find the mean, I simply add all those and divide it by 16. Okay, this is the sample mean with us. Now what is the question? Question is find the probability that this particular x bar falls between 4.6 and 5.4. So we are worrying about to find probability of
4.6.
and this x bar
5.
should be in between
5.4.
4. Okay, we just wanted to find this.
So
Now
we
how do
can
we find it?
standardize the mean then.
Yeah, we will just standardize this, you know. Right?
Yeah, x
So
minus mu by
if we
sigma.
know y is this, y minus n mu by sigma root n follows
Yeah.
normal 0 1, standard normal.
Yeah.
Right? This we know. Right? And this x bar is nothing but y by 16. Right? This sum is y. I consider this sum as y, and that is and this my x bar will be equal to y by 16. So simply what I have to find is probability that 4.6 is less than or equal to y by 16, which is less than or equal to 5.4. Now I just have to standardize this. I just have to bring this. Now n here n is 16, mu is 5, sigma is 1. So we have values of n, mu and sigma. I just have to bring that in that form. So what I do is I just multiply 16 both sides, or you multiply 16 both sides, what you will get? Probability of, if I multiply 4.6, 16, 36, 27, 6, 4, 6, 13, 73.6. So 73.6 is less than or equal to y less than or equal to 16 times 5.4 will be 4, 6, and 8. So this will be 86.4. Just do these computations. Just check whether I'm correct or not.
Yes, sir, you're correct. Absolutely correct, sir.
Yeah, this y will lie in between 73.6 and 86.4. Now what I have to do, I have to subtract n times mu. So n is 16 and mu is 5. So I just have to subtract 80. So 73.6 minus 80 less than or equal to y minus 80 less than or equal to 86.4 minus 80.
Yes, sir.
Right, I'm just standardizing the things. I'm just bringing in standard normal. I'm just converting this particular random variable y to standard normal. So now this is minus
6.4.
6.4 less than or equals to y minus, see this is 16 times 5, which is n times mu.
Yep.
And this is again 6.4. Now what we have to do, we just have to divide it with sigma root n. So sigma is 1 and root n is 4. That means we just have to divide it by 4. So once I do minus 6.4 by 4 less than or equals to y minus 16 times 5 divided by root 16 into 1. So this is root n times sigma. This should be 6.4 by 4. So if I divide 6.4 by 4, 1 times 1.246. So this is minus 1.6. And this becomes my standard normal. This is just the notation of standard normal random variable. So this becomes, this is of the form y minus n mu by root n times sigma. Now this is z, which is less than or equals to 1 by. So now this is easy. Fz of 1.6 minus fz of minus 1.6. Okay. So I guess the values are given to you.
Oh, yeah. The
You
answer will
know
be
the value of
0.89.
1.6. Right. So it is given the value of 1.6.
Yeah, yes, sir.
So
It
this
is
is
0.59452.
This is minus 1.6. How do we get the value of fz of minus 1.6 if you know the value of 1.6?
Subtract from 1.
Yes.
Yeah, correct. See, this particular 1.6 is the area under this curve. So fz of 1.6 is this, right? Probability that x takes y takes z takes value less than or equal to minus 1.6. So that means that is this region. So this region is same as this region. So this red region is nothing but 1 minus of this whole green region. This whole green region is given to us, which is fz of 1.6, which is probability that z takes value less than or equal to 1.6. So this particular green is given to us. We just have to find the red. It is 1 minus of that. So this is, if you compute, this is given to us 0.9452 something. You just subtract 1 from this. So 1 minus 0.94, 0.0548, right? Just check some, maybe I can do some wrong. Okay, just check the values, just subtract this, it's just a subtraction. Just if I subtract this, this will be 8
Okay,
and 9, 4,
Yes,
2.
it is the answer, sir. You are
Sir, it's in the range of the answer.
Yeah. So 0.8904. So something. So yeah, whenever the values are going like this, so you don't worry about the what will be the fourth decimal or fifth decimal. We don't usually ask more than 3.
Oh,
Yeah. So this is how we find the first question. Okay.
okay, sir. I got confused at that portion y by 16. So
Yeah.
I didn't got the answer.
So we are worrying about the mean of the sample. Okay. We are not considering the whole sample, whole
Okay.
life of the sample. We are worrying about the mean of
Okay.
that sample. Okay. And what about the question number 3 here? So what that
It is
I
some
think
similar type of
it's
question.
similar. So
yeah, similar kind of thing. So here it is some an electrical firm manufactures. Yeah, the same thing. We have given you the mean as 600, standard deviation as 50. So sigma is 50. Find the probability that random sample of 25 bulbs will have an average life of less than 615 hours. So here the inequality is
Follows the Poisson random variable.
and it is given as Poisson. Huh?
Yeah.
No, it is given as normally distributed only.
Acha. I've seen the.
That's question 4.
Okay, sorry.
Yeah, question 4 is Poisson.
Yeah.
But the key idea is all these questions are of depends on central moment. Okay, you just standardize the thing, identify what is your y. Once you identify y, once you identify what is n, once you have the values of mu and sigma, just standardize it by y minus n mu by root n times sigma. Using that, just standardize it.
So the question 2 will also go like the question 1.
Question 2 is random. Oh, okay. Here it is discrete, right?
Yes,
So for
sir.
this you have to compute mu first, right?
Yes, sir.
Once you compute the mu, then it is the same thing, same problem.
Okay, sir.
Okay.
Thank you, sir. Thank you.
Okay. Thanks. Okay, then let us go to 7.8. So what is the time span?
Sir, excuse me, sir.
Yeah.
Sir, can you solve the 7.6, question number 6?
7.6, question number 6.
The
Okay.
sixth moment, I can't find that. It is given the question of what is the value of the sixth moment of normal. The mu is given 0 and the standard deviation.
Okay, got it. So
It's a small
sixth moment of normal 0.3.
Yes, sir.
Right. Okay, now here we know sigma square is 3. So in order to get the sixth moment, what we do is we follow the stepwise procedure itself. What is the moment generating function for normal?
It is
e
sigma
to the
square.
power. So when mu is 0, so sir mentioned lots of times, I guess, even when I woke up you at night 1 a.m.
Yeah.
You should be able to tell what is the moment generating function of normal 0 sigma square.
Yes, sir.
So what is that? You tell me. Now you are awake and you are sitting in the session, so you should be able to tell me. Anyone?
Sir,
we'll expand this.
3 lambda square by 2.
No, sir. It is like
lambda square
sigma square by 2.
Yeah. So here we know that sigma square is 3. So it will be 3 lambda square by 2. So what is the expansion of e power x?
Sir, 1
plus x plus x
square by 2. Yeah. Like this it goes.
1 plus x square by 2.
Right.
2 factorial.
Now here, right, correct. Here x is 3 lambda square by 2. Just substitute that. I will get 3 lambda square by 2 is equal to 1 plus 3 lambda square by 2 by 1 factorial plus 3 lambda square by 2 whole square by 2 factorial plus and so on. So we want the sixth moment, right? So it should be
3 lambda
something lambda power 6.
Third term.
So 3 lambda square by 2 whole, yeah, this is that, by 3 factorial. And next one will be and so on. So this is something like 1 plus, we don't need to worry about this. Just worry about this 3 cube by 2 cube into 3 factorial into lambda power 6. But what is the, so now this is the question of, if it is e power lambda x, so what will be this thing? 1 plus
lambda x.
So what is the sixth moment of sixth moment is expectation of x power 6,
Okay.
right? What is the first moment? Mean. What is the second moment? E power x square. Third moment e power x cube. Fourth e power x power 4. So
Okay,
these
sir.
are the moments, right?
I didn't know this, sir.
Hmm?
So I didn't know this. I'm getting.
Okay, this was explained in the lecture, right?
So I didn't watch that carefully.
Okay. Just watch that. These are moments.
Yes, sir.
Okay, these are the moments. So how we will get these moments is, these are nothing but the coefficients of, so if I want kth moment, kth moment is coefficient of lambda power k by k factorial. Okay. So remember this, kth moment will be coefficient of lambda power k by k factorial. And that particular coefficient will turn out to be equal to expectation of x power k.
Okay, sir.
Okay. And this kth moment is equal to expectation of x power k, and which is equal to coefficient of lambda power k by k factorial in your expansion of this particular term, e power this particular expansion. So just identify lambda power k by k factorial. Now I have lambda power 6. I just want divided by 6 factorial. So what I do is I will multiply by 6 factorial and divide it by 6 factorial. Now the coefficient of lambda power 6 by 6 factorial is this, right?
Yes, sir.
So this is the sixth moment of normal 0, 6. So if you compute the value, I don't, I think it's a larger value.
Yes, sir. 405.
Okay, then it
405.
is smaller only. I thought it will go around some 30. So this is 6 times 5 times 4 by this 3 factorial gets cancelled. This is 2 into 2 into 2. This is 3 into 3 into 3. 2, 2, 2, 2, 3. So this is 3 power 4 times 5. 3 power 4 is 81 times 5. This is 405. Okay.
Yes, sir. Thank
Okay.
you, sir.
Just get this. Just watch the lecture. Sir has explained this. How this kth moment will be equal to e power x, expectation of x power k.
क्या बाउंस है, शरीर के पास गेंद छोड़ सकते नहीं, खेलना पड़ेगा आपको बाहरी किनारा। आराम से बॉल गया स्लिप पे, इसे आप खेल रहे हैं ऑस्ट्रेलिया में कि उछाल के साथ बॉल जा रहा है और स्लिप फील्डिंग आसान।
Okay, I just muted everyone. Okay, this is how we will get the sixth moment or kth moment. Any moment, any kth moment can be found out like this. So it is just the coefficient of lambda power k by k factorial. Once you have the expansion, just try to get the lambda power k by k factorial term and get the coefficient of it. So that will be equal to your kth moment. Okay. Okay.
Yes, sir.
Okay.
Thank you, sir.
Okay. Thank you. So then let's move to 7.8. So what is the timestamp of 7.8? Apple.
Yeah, so Venkatesh, the question is, what is degrees of freedom? I mean, I can tell you the timestamp, but the specific question is, what is meant by degrees of freedom?
Degrees of freedom is independent, a number of independent variables present in that particular equation.
equation. Okay. It is at 9.15. That was the question only. What does the degree of freedom mean actually?
9.15.
15.
Okay.
So the question was, what is n degrees of freedom? That is what I wanted to understand.
Yeah. See, here there are some x1, x2 to xn, which are independent, right? Independent of all other values. So here n gives me the n tells me there are n independent what I say n independent
Terms.
variables kind of thing. Okay. So even if this comes in sample variance also, if you remember, when sir is talking why we divide it by n minus 1 instead of n, there also professor has mentioned that actually the xnth term is can be found out from the xn minus 1 terms, all the xn minus 1.
No, I mean, I understood that n term, but the word that was used was degrees of freedom.
Degrees of freedom is, as of now, it is same as an independent
variables.
Variables kind of thing.
Okay, fine. Thank you.
Yeah. Any other doubts specific to week 7 or from week 6 or previous weeks? So I can see many of you haven't gone through video lectures. So that is why you guys are not having any doubts. Okay. To make this session a little more interesting. So why we divided by n minus 1, as we have just spoke about the sample variance.
That's because n minus 1 becomes independent. If we have n, they have dependency.
Okay.
We need to have IID, and if we are taking n minus 1, it is not independent because of what we had studied earlier. I mean, it's a loose definition, but that is what I understood from the lecture also.
Okay. Okay.
Is that right? Wrong?
It is okay. See, we
Yeah.
can have many explanations, but there will be some solid explanation for right. So when I have s a square, are there any other doubts? If no, I will just discuss this for 10 minutes and we can end the session.
Sir, I have a doubt in MGF.
Okay. What was the doubt?
So my question is like, in case of discrete random variables, like we can get the distribution from the MGF. What are the probabilities? So can this similar thing be done in case of continuous random variable? I didn't get no explanation, no examples were there in the lecture for continuous random variables.
Okay. Can that be done?
Sir, I don't know.
Okay. So I will give you one MGF. Can you give me what distribution will it follow? Okay.
Yeah.
Any
Sir, normal.
Normal?
With the standard, with variance 9 and mean 5.
Okay. So is it just the guess or?
No, because E sigma square lambda square by 2 formula is matching with this one.
Okay, but I have written it wrong. It will not be normal.
Okay.
See, normal is mu lambda plus 30. Okay. So this is even I don't know. I just gave the distribution. This is not a, you cannot get the standard kind of thing. So this is, if I have given you 5 lambda plus something, this will, now this will follow normal 5 comma 9. Okay. If I have given lambda here, then it is normal with mean 5 and 9. So if I have given you something like this, it's very hard to get the distribution of this function, of this random variable. Okay. Even I don't know what the distribution of this is. This is not a common distribution that I can guarantee you. But getting distributions for continuous function is a little harder than discrete case. Okay.
Yes, sir. Okay. Thank you.
So,
Sir, I have a doubt in central limit theorem. So can you briefly explain the statement of this theorem and how do we use it to approximate probability? That's where I'm facing trouble.
okay. So central limit theorem is actually used to for if you have any random variable which follows some other distributions where we cannot actually find the probabilities, or where we cannot actually find the distribution curves or probability density function or CDF in a closed form. If you are unable to find that, it will be difficult for me to visualize the data. So it is very difficult for me to talk about properties of that random variable or kind of thing. What we do is, what we assume is, if you have any distribution, whatever maybe your distribution is, I can actually convert that particular distribution approximately to a standard normal, which is well-known distribution to us. So that is what CLT does. So if I have some n IID samples, some IID samples of some distribution X. So I don't know what X is, how it is distributed, but what I know is it has some mean mu and variance sigma square. Okay, I know only these two things from this distribution, but I don't know how exactly this is distributed. It can be like this, around treat it as mu, and it can be like this, it can be like this. So all these curves will approximately have mean at mu, and also variance may be equal to sigma square kind of thing. So this is sigma, this is 2 sigma, and all the values may lie in this thing. But in order to calculate the probabilities, it will be difficult for me to compute integrals of these curves, right? Area under these curves will be difficult for me to compute. So that is why what we do is, we just convert this particular distribution approximately to standard normal. So what we do is, we shift this to, actually we shift this mu to 0, and we shift this curves approximate to normal 0. So like this. So what we do is, we just convert these curves, approximate these curves to inverted U shape kind of thing. So any distribution can be done like this, but these are only approximations, not the accurate one. So we'll try to approximate
So
this.
any IID X having mean mu and variance sigma square will always approximate to normal.
You can always approximate to standard normal 0, 1. Okay. How we will approximate is, that is what CLT tells us, central limit theorem tells us, and this CLT is valid only if our n takes larger values, like n greater than or equals to some 30. Some say 30, some say 25, but it should be a larger values, not like when n is some 2 or 3 or some 10. A good approximation. So when n is larger than 30, we can actually approximate any distribution to standard normal. So what we do is, first we shift this curve to to for making it to be symmetric around y-axis, which is nothing but
Zero mean.
zero mean. So what we do is, first and foremost step is to shift all the data points such that expectation of this x is 0 and variance remains the same, sigma square. Once you get this, so once you bring our data points nearer to 0, what we will do is, I will take a new random variable x such that it is equal to x1 plus x2 plus and so on plus xn divided by root n. Okay, this particular thing follows. So I consider this x1 plus x2 plus xn by root n. Now this particular y follows normal 0 sigma square. Okay, so if I have x1 x2 and so on xn, some n samples with me, I add those all samples and divide it by root n, so which is a new random variable, because x1 x2 xn are random variables. Sum of some n random variables is a random variable, and I divide it by root n, and this particular new random variable y follows normal 0 sigma square. So that is what central limit theorem tells me. So when I have some n distribution,
So this step of doing the expected value to 0, so why is it crucial?
see, we don't want to always see, if you decrease one parameter, it will be easier to look and visualize, right? So if your mean is around some 70 or 80, so looking the distribution around there is same as looking the distribution around 0. So when we have one parameter becoming 0, for our calculation purpose or whatever, calculations will also be easy. Okay, see, so you know how to compute the distance between 2 points. So if there are 2 points, 1 comma 2 and some minus 1 comma 2, so it will be easier to compute the distance between these 2 points from 0 comma 0 than you have something 320 comma 410 is 1 point, and you wanted to compute distance between the same points. Okay, this will be root 3 root 3. So there are some 2 points, but if I can move this point to 0, it will be easier for me to compute the distances than computing distances there itself. You can do that, but bringing that to be in between will make our calculations easier and life easier.
Okay, so this is regarding only the calculations. Even if we keep the mean as mu, we can approximate this distribution to normal. That will not be an issue.
No, see, standard normal takes values in between with mean 0 and standard deviation 1, right? It will be like this. So if you wanted to compare this particular thing to some distribution here, it will be difficult. So just bring this distribution, bring this distribution to here and look how it is changing, and then approximate it to standard norm. So if both the distributions are very near to each other, then it will be easier for us to even visualize or even computing values also.
Yeah.
So this is this will follow normal 0 sigma square. Now if this follows normal sigma square, what we get is I just simply subtract it with, so this particular thing, when y, now this is new y. Now I'm just defining y as x1 plus x2 plus and so on plus xn. So now I have taken the sum of all the n random samples. So this is my y now. So if this is y, what I will do is y minus n mu by root n sigma follows normal 0 1. So even this is also CLT. So if I have x1, x2, xn comes from IID some different distribution, and I will look at a new random variable which is the sum of all the random samples, random variables, and random samples, and random variables, sorry. So once I look at the new random variable y, now this y minus n times mu, where mu and sigma are standard deviation of x and mean of x, so expected value of x. So if I know this mu and sigma, y minus n mu by root n times sigma follows normal 0 1. And also luckily every distribution can be converted to normal, standard normal 0 1. Every distribution, either it is binomial, either it is Poisson, either it is Bernoulli or exponential or anything, gamma, beta, everything, by changing the parameters, some parameters, we can actually bring, or we can actually compare, or sorry, we can actually bring every distribution to standard normal 0. We can actually convert it.
Here are two things. First, we say that IID x with n greater than equals to 30, we can approximate this distribution to normal distribution.
Normal distribution, yeah.
And secondly, we are saying that one random, the summation of these all, considering it to y, and this expression is normal, standard normal.
Right. Right.
Okay.
So once we convert into standard normals, we have many tables to get the probabilities of the smaller regions. So each and every probability can be found. So this is standard normal 0 1. So this probability you can find. This probability you can find. Actually, we know the cumulative distribution function of standard normal 0 1. So you can actually compute a smaller areas which will be equal to the probability of that particular region, probability that x takes values in that particular region is equal to area under that particular curve, under that curve normal 0 1. So it will be easier. Now once you convert any random any distribution to standard normal, we have lots and lots of formulas where we actually get the probabilities. So that is why we convert. Okay, I hope some points are clear to you.
Yeah, got it, sir. Got it.
Hello, sir.
Yeah, hello.
Sir, in case I couldn't like do any assignment or weekly graded assignment or attempt the quiz properly, I am like I am just going to start my statistics syllabus. So how should I go about it?
You are about to start week 1 or week 2 kind
Yes,
of
sir.
thing.
Week
Okay.
one.
Okay, do one thing. Okay, you can start from week 7 right now. Okay, there is no I don't say there is no connection, but from week 7 we will be introducing new we will be discussing new descriptive statistics kind of thing, so which is more or less independent from the weeks before. Okay, till week 6 we just discuss what all the distributions and some common means and variance of some common distribution, some discrete distributions as well as some continuous distribution, some joint PMF, some joint distributions, marginals, conditionals, and everything we discussed only on some few well-known distributions. But from week 7 we actually deal with statistics, data, and everything. So if you are starting new, start with week 7 because you can actually submit the assignments now. Okay. go with the flow, and later if you have some time, if you got some time, start with week 1. So how will you give, are you going to give quiz too?
Yes, sir. I want to give quiz too. Even in quiz one, I just went and I just plugged the answers and gave back. I got around 50%, 48 or 50% in the quiz one.
Okay, just plugging you got 50%, but why is the pass percentage of statistics is 57?
Huh?
I don't know. See, the thing is, you just went sat and you just plugged in the options, you got 50%.
No, sir. But I am from a tech engineering background. But I would have to say that.
Okay, okay, fine. Okay, in that case, you might have some knowledge, right? Then you might
Yeah.
have done numerical methods.
In first semester, I performed well, but in second semester, due to the college pressure, I could not even open the dashboard. To be honest, in this
Okay.
week only, randomly I started. So from now I will be able to continue well.
Okay, then start with week 7 directly. Don't worry about till week 6. It will, for you, I guess, watch video. If you want to watch video lectures, watch it in 2x and just solve activity questions or just solve graded assignment questions. If you are able to solve the graded assignment questions, it's fine. So try to solve all the weeks 1 to 6 graded assignment questions. If you are unable to solve those, just go back to the practice assignments. If you are unable to solve those also, then go back to activity. Even then, if you are unable to solve, then go back to the lecture, watch it in 2x, you will definitely get.
Okay, sir. All right.
Yeah. So, but focus on week 7. Start from week 7, submit assignments from week 7. Okay.
Sure.
Okay.
Yes.
Sir,
Since week
in this
7,
week,
one by one, please.
yeah. So, sir, in this week we studied about various type of new distribution, that was gamma and beta and Cauchy. So, will we discuss this again in further weeks, or this is it? Because we didn't go very deep
No,
into it.
we are not interested to go in very deep regarding this gamma. And
Okay, these all were for just for introduction.
yeah, see, in week 8 you will see a complete new things. See, from here onwards, every week will be new to you. So next week, I think you will get week 8 contents by now. So next week we
so
are going
week
to
8 contents are in the dashboard.
It's already released. Huh? Okay. In there you will see something we estimate parameters actually. So parameters. So we have parameters for every distribution, right? So in week 8, what we do is we actually estimate we actually estimate an error. What we say is, if you know the parameter, you are calculating probabilities here and everything. You are calculating the moment generating functions. You are calculating CDF, PDF, and everything based on the parameter. There we actually estimate the parameter. So you don't know the parameter, but we try. You have the distribution with you. We try to predict the parameter. Okay, there you see new things. And week 9 is different. Likewise. So everything is interconnected, but you will see new things in every week. Till week 6, you might be very. The content might be very slow. So it's just for refreshing you, sitting, make you comfortable with stats too. But now on,
So
we
even
actually
if the speed was slow, but we struggled there as well. So how do you say to go about these new things and further weeks?
Okay,
And
see,
so the
maybe
length of the video has also increased a lot.
yeah.
Yeah.
Okay, the thing is, as you are seeing for the very first time, I think that will be a difficult for you. When you revise the things, you will feel weeks 1 to 6 are very easy, and from here, actually, it is theoretical. My personal opinion is theory is difficult than computing problems. So that is why I said till week 6 it is easier, and from week 7 you have to new terms will be introduced every lecture, and you have to go through those new terms. Yeah, that is why I feel from here onwards you have to be very keen on every lecture, keep an eye on it, and keep an eye on every lecture, follow every lecture. You might miss some new term professor has introduced, and you might don't know what that term is. Then it will be difficult for you to solve the problems. So that is what my intention. I don't say this is also difficult, but term each and every lecture will have lots and lots of new terms coming into play, and you have to understand every term. Once you understand, you can answer. You will be able to answer. And some might feel these lectures will be easy than the previous. Just
Sir, the
one's
previous
perception.
weeks are the previous weeks interconnected with the coming weeks?
See, we actually use the distributions of some common random variables. Okay. So those distributions, you have to know what conditional. We will use conditional densities.
Quiz 2 will contain 1 to 10 weeks.
Quiz 2 is from 5, 6, 7, 8. But it may also contain weeks 1 to 4, because weeks 5 and 6 are something interconnected to week 4. So as we say, week 6 is a refresher week, right? So there we have some liberty to ask you from weeks 1 to 4.
Yeah.
Okay, but more focus on weeks 5, 7, and 8.
Okay.
Okay. Yeah. So any other doubts?
Hello.
Hmm?
Can I ask one doubt from week 5? Yeah.
If there are no doubts in week 7, I will take doubts from previous weeks. Yeah.
So in the graded assignment, I solved the question number 3 and 8, but I don't know why the answer is wrong. Can you give me some hint why?
So have you got the solution PDF?
Yeah, solution is there, but the values are different. Whatever you posted on the, you can say, drive.
Okay, it's a parameterized question.
Parameters are different. But I try by that approach also, your approach, but I'm getting different answer, and the answer given in the solution, that's a different.
Open. So week 5 graded assignment question number
3 and question number 8.
Okay.
Can I share my screen?
No, just tell me, just read the question number 3 out. You can.
Okay.
First lines maybe.
It's the question is something like this one. The joint PDF of two continuous random variable x and y is given by, the function is given here, f of x comma y, that is equal to 4xy divided by 5 to the power 4. The support is here 0 is less than equal to x is less than equal to 5, and 0 is less than x 0 is less than equal to y is less than equal to 5, and 0 otherwise. Okay, and we have to show that x and y are independent. Okay, so since in the denominator we have 5 to the power 4, that's why the value of fxx and the value of fyy, the product of this is not equal to the actual function.
Okay, so let me solve it then.
Yeah.
Okay, I will take your values only. Just tell me f of x. What is x of xy?
That is 4xy divided by 5 to the power 4.
4 xy divided by
xy divided by 5 to the power 4. 0 is less than x is less than 5, less than equal to, and y also 0 is less than equal to y is less than equal to 5, and 0 otherwise.
Okay. So what we have to compute is we just have to find the marginals and product of marginals. Product of marginals should be equal to this. If it is equal, it is okay. If it is not equal, then they are not equal.
Yeah.
So how will I get the marginal distribution of fx?
So
have to integrate it from 0 to 5.
0 to 5.
4xy 5 power 4 dy.
Dy, yeah.
Right. So
Yeah,
4
that's correct.
by 5 power 4 I can take 4x by 5 power 4 I can bring it out.
Yeah.
Because all these are constants.
With respect to y variable, yeah.
0 to 5, yeah, y dy. So this is just the y square by 2, right?
Yeah, y square by 2.
And it will be 5 square by 2.
Yeah, 25 by 2.
Okay. 4x by 5 power 4 into 5 square by 2.
Yeah.
This will be 5 square and this will be 2x. So I get 2x by 5 square.
Yeah.
And 0 is less than or equal to x, less than or equal to 5, and 0 otherwise. Right? This is the marginal distribution.
Okay.
And what will be the fy of y? Same thing. Now I can take a 4y by 5 power 4 outside. So this is 0 to 5 x dx. So 4y by 5 power 4 into same thing x square by 2, which is 5 square by 2. Now this will be 5 square. This is 2y by 5 square. 0 less than or equals to y less than or equals to 5. Okay. Or it is 0 otherwise. So now what I have is product. If I product these two, I will get 2x by 5 square.
Okay. Yeah,
2x
it's
by,
correct.
so 2x by
Yeah.
5.
I got it. Sorry, I got it.
This will be 4xy by 5 power 4, which is
The same as the, yeah. I didn't simplify. I put this 50x by 5 to the power 4 as it is.
okay.
Okay, that's why I'm
Okay.
getting.
What is 8?
Yes, sir. The
Another,
eighth one is.
is it like the amount of milk?
Yeah. The amount of milk, something like that one.
In a shop at the beginning of any day is a
Yeah.
random amount.
Yeah.
X
So we
from
have to
which
evaluate x minus y is less than 6 here. You have the question, or I have to say the complete question?
What is the distribution? Density function? Is it 1 by 50?
Yeah, 1 by 50. 0 is less than equal to x is less than equal to 10, and 0 is less than equal to y is less than equal to x, and 0 otherwise. And then we have to evaluate the probability which is less than 6 liters.
6 liters. Find the amount of milk left at the end of the day.
Yeah, less than equal to 6 liters. So I got the answer as 0.42, but in the question it is given 0.82.
Okay, what we have to find in terms of x and y? Just tell me what we have to find in terms of x and y.
You have to evaluate probability of x minus y is less than 6. P of x minus y is less than 6 because x is initial amount of milk, and y is that is sold already or in the end of the day.
Right?
Yeah.
So I can write this as okay. Now I have joint density with me, which is 1 by 50 in the interval. So I just draw the region of it. Okay. So y is in between 0 to x, and x is in between 0 to 10. So the region will be this. Right?
Yeah, 10 is there. Yeah. X is 10, y is 10. Yeah.
So this is the lower triangle is the region for me.
Yeah, right angle triangle.
So in order to find the probability that x minus y is less than 6, I will just draw the line x minus y is equals to 6, and I will find the region where x minus y is being less than 6. Okay.
Yeah.
So how will my x minus 6 is equal to x minus y is equals to 6 line look like? And x is y is 0, x is 6.
Yeah. You can say it's a parallel to the line y equal to x,
0.
something like that.
Just correct me if I'm going wrong. So I think the line will be something like this.
Intersect this line x equal to 10.
It won't intersect. It will intersect, right? When x is equals to 10, my y is 4, so it will intersect here. Okay. Yeah. So now tell me which region is x minus y less than 6. Is it above this red line, or is it below this red line? Okay, just substitute 0, 0 comma 0 in it. So if that inequality satisfies, that means 0 comma 0 will lie in that region.
Yeah,
So if
it's
I
less than
substitute 0
6.
and 0, 0 is less than 6, it is true.
Yeah.
Right? So that means this particular region belongs to x minus 6, x minus y
Yeah,
is
yeah.
less than 6. Okay. Now this red and black intersection is our region, common region, right?
Yeah, this common region.
So this is, if you find the area is also fine. Find the area of this and divide the areas. It's fine.
Yeah.
So in order to find this area, just find the area of this and subtract it from. So area of the bigger triangle is
1 by 2 into 10
50.
into 10.
Yeah,
Yeah,
it is
50.
50.
Yeah.
See, as it is distributed 1 by 50.
Yeah.
So you can, from there also you can directly get. It is uniformly distributed.
Yeah. And the area of a smaller triangle is 1 by 2 into 4 into 4. Hello. Hello.
Disconnected.
Yeah.
Okay, sorry. I just got lost connection. Annoying. I don't know what happened. Am I audible?
Yeah, you are audible.
Yeah. Sorry. A host can you make me co-host again? So did you understand that thing? Just find the area. Who is that?
Yes, sir.
Yeah. So
So
find that area, divide the
area,
areas, you will get the probability.
the area of lower triangular is, you can say, 1 by 2 into 4 into 4 because
4
the
into
base
4.
is
That will
towards
give
4.
you 8, right?
Yeah. So the answer is I'm getting 0.42, but in the answer it is given 0.82.
84. See, the area is 42 now. So the required area is 42 now.
Yeah.
But the original total area is 50. So the probability will be 42 by 50, right?
Okay.
Now it is equal to 84 by 100. Okay, I got the co-host X. I don't know, sometimes Zoom will quit automatically and it will be difficult to log in. So the total area is 50 and the area we want is will be 42. So therefore the probability that x minus y will be less than or less than 6 will be equal to 42 by 50.
Okay.
So the required area divided by
Yeah,
total.
I understand where the mistake. I consider this because the red region is going above, na? So I consider this complete because the y value is 10. So I consider the complete region. Okay,
No.
not the triangle. We have to break up to this green triangle, na?
Right.
Okay, that's my mistake. Okay, thank you, sir. Thank you.
Okay, then we shall end this session if there are no doubts in week 7.
So in week 7.6 in question 4,
Mhm.
it is mentioned that there will be more than 33,000 3,300 accidents in a year. So this will be the sample mean, or we'll be taking the y.
Which question is it?
Question number 4, 7.6. Like in question 1, we took y by 16 and then equated to the 4.6 and 5.4 values. So here we will directly take 3,300 now. Okay.
So now n mu will be okay, you directly take 3,300 and your y should be greater than 3,300.
Yeah,
So you have
yes,
to
sir,
find the
yes.
probability that y is greater than 3,300.
Yes.
Right.
Okay.
Okay, then thanks for joining and have a good day.
Thank you, sir.
Thank you, sir.
We will meet
Thank you,
next
sir.
time. Yeah.
Thank you, sir.
Thank you. Host, you can end the session.
Yeah.
Who said yeah? Is it host or someone? Okay, host, you can end the session. I'm leaving. Thanks, guys. Thanks for joining.
Thank you, sir.